Welcome to the second presentation in Unit 2. This is called Molecular Geometry. The learning goals for this presentation are that you understand the arrangement of atoms based on electron domains, that you understand hybridization theory to predict bonds, that you understand the wave nature of electrons as it relates to molecular orbital theory, and that you be able to predict the structure and number of bonds based on molecular orbital theory. So, molecular shapes. Molecules, covalent compounds tend to form specific shapes, and you can determine those shapes experimentally using X-ray crystallography, neutron diffraction, or electron diffraction. That will actually give you the structure of the particular molecule. This right here is a famous picture of DNA, and it was only using this particular structure, this particular image that was found in another lab, that Watson and Crick were able to deduce the fact that DNA is a double helix structure. Without observing this particular picture, there's no surety that Watson and Crick would have been able to determine the structure of DNA without some sort of outside guidance. So there's some thought that they stole the idea of the double helix, but the people who had this particular structure had no idea what it meant at the time. So you go back and forth on that one. You can also use neutron diffraction and electron diffraction. So, molecule shapes. Molecule shapes can be predicted by lone pairs and by bonding pairs, which include multiple bonds. So the shape of the molecule plays an important part in the reactivity. For example, if this is a positively charged center molecule, and I have a negatively charged atom, it could come in here and it could attack this atom, and it could actually have a chemical reaction. If you contrast that with if we take this same molecule and we were to surround it with a whole bunch of other molecules, and I know we're violating the octet rule, and it's still a positive charge, it's a lot harder for this negative charge to find a way to get to the central atom, so the molecule shape can actually play a really important part in reactivity. So why that shape? Electrons will always repel each other. Even the electrons in a particular bond will repel each other. So the bonds tend to spread out as far away as they can from one another, and they adopt their molecular geometry as a result of that repulsion. So predict the shape of a molecule with 9 atoms connected to a central atom. So this is kind of an exercise in creativity. I've got a central atom and I need to connect 9 things to it in a way that separates the atoms out as far as possible. So the first thing we want to do is we want to say, okay, I'm going to put one here and one here and one here and one here. That right there would represent 4 particular bonds, but those 4 bonds, even though they're spread out fairly well, wouldn't be realistic if it was 4, because we have to look in a 3-dimensional shape. So I'm going to add 2, kind of coming out of the page, going into the page, and then I'm going to do the same thing on the opposite side. I'm going to say this is going out of the page and into the page. And so that actually gives us a total of 8 bonds. The problem is that we're still missing one more, which is why this thing becomes notoriously difficult. The last one is going to be connected somewhere like right here, and is it going to shift everything to the left just a little bit. So it's no longer going to be a homogeneous shape because of the fact that it has 9 things connected to it, as opposed to 8 or 4 or something that's easy to work with. In this question it says calculate the difference in electrostatic repulsion when an electron is placed at X or placed at Y. So in this one you actually have to do some calculations with Coulomb's law. Now some of you aren't familiar with Coulomb's law, so here's the equation. It's F equals K Q1 Q2 over D squared, where D represents the distance between 2 things, and then you have Q1 and Q2 representing the charge. So the first thing that you should realize is no matter what this particular situation is, we're talking about the electrostatic repulsions between 2 electrons. So if I were to put the first electron right here, let's start with this as X, and here's my original electron. Okay, that's easy because the distance would be 10 angstroms. And I could easily calculate this out using the formula F equals K Q1 Q2 over D squared. Q1 represents the charge of an electron, and every electron is charged with 1.6 times 10 to the minus 19th. So it doesn't matter if I have 1 or 2 of them. They all have the same charge. So the second charge is the identical 1.6 times 10 to the minus 19th. And some of you may be saying, but the charge of an electron is negative, and that's true. It should actually be negative. But when you multiply the two negatives together, they're going to cancel it out. K is a constant. It's the electrostatic constant. It's 8.99 times 10 to the ninth. And then the D is the only difference between these two particular terms. For the first D, I'm going to say that it's 10 angstroms. And angstrom is defined as 10 to the minus 10th. So when I do 10 times 10 to the minus 10th, that's really 1 times 10 to the minus 9th. Okay, so that's our first indication of this. And then at that point, we would go ahead and look at the other value. In order to find the other distance, the distance for the second term, you can't look at this distance. You're trying to look at the distance between these 2 points right there. If you look, I have a triangle. You have 5 angstroms and 5 angstroms, which means that this is going to be 5 radical 2. If that's 5 radical 2, we now have our distance for the second trial is going to be 5 radical 2 times 10 to the minus 10th. And some of you are going to say, what, 5 times 2 radical 2? You can go ahead and simplify it. 5 times radical 2. Radical 2 is like 1.414. So you can go ahead and figure out what it is from there. So that ends up being something like 7.07 times 10 to the negative ninth. Okay. 7.07 times 10 to the minus 10th. Okay, so now that you have this, you can take your numbers and you can plug them into Coulomb's law. Okay, when you do that, you're going to get force values that are going to be very, very different. Okay, the first force value you're going to get is going to be something like 2.3 times 10 to the minus 10th newtons. That's the repulsive force between these two electrons. Now these two electrons right here are closer together. Now they're not exactly half because of the fact that it's at an angle, but if you were to look at this, this would give us a value of something like 4.6 times 10 to the minus, let's see, to the minus 10th. And somebody may be saying, well, wait a second, how did that work out? It's the fact that you have that radical 2 term there. And it just has to do with the angles that are set up. You should be able to plug these numbers in and get these values for the electrostatic force. Next, electron domains. Electron domains represent either a lone pair of electrons or a bond. Multiple bonds, whenever you have 2 bonds right here, that does not count as 2 different electron domains. Only the sigma bonds count, which stands for the single bond. So this right here represents a single electronic domain. So how many electron domains surround each atom? If you were to look right here, you have the electron domains right here. You have 1, 2, 3, 4 electron domains. 1, 2, 3 electron domains. 1, 2, 3, 4 electron domains, and 1, 2, 3, 4 electron domains. Coulomb's law. We've already learned that objects repel, like charges repel, so electrons want to move as far away from each other as possible, and that determines what we call the molecular geometry. So we use valence shell electron pair repulsion theory, or VSEPR, to predict a molecule's shape based on the valence electrons and the bonds that are there. Okay, lone pairs tend to push electrons more than bonded electrons. So for example, if I were to have something like a central atom, let's call it nitrogen, and I were to have 1, 2, 3, and then a lone pair, the lone pair would push these electrons and the bond angle would not be the same between all of these. So this would be a larger number. It wouldn't be 109.5 like it's supposed to be. This would be something like 112, and all of these would be smaller because the lone pair will push more than a bonded pair. So let's look through the different shapes. So you have a linear shape, and now what we're talking about is we're talking about molecular geometry, not electronic geometry, which we'll distinguish between. Molecular geometry refers only to the bonded atoms. So we're not talking about the fact that there could be electrons on top or below the central atom. So if 2 bonds are present, they will repel each other. You get a bond angle of 180 degrees. An example of this is beryllium chloride, and so this right here would represent a linear molecule, okay, because these right here are getting as far away from each other as they can. Next, we can talk about non-bonding pairs in the bond angle. So we talked about the non-bonding pairs are physically larger. They occupy more space because they don't have as many restrictions on their position because of the bond. So the repulsion tends to be greater, and whenever you get something that's greater, we can predict exactly what was said here, explain why the unbonded electrons have a greater bond angle between them than the bonded electrons. Now this is an example we already went over, so you should be able to do this. Now if you can't do it, you need to refer back to the earlier part of the video. Now bent is an example of something in which you have a lone pair of electrons on the central atom. If you have two bonds with a lone pair present, they will repel each other, and you get this. Now once again, I know that I have some sort of lone pair here, but that lone pair doesn't have anything to do with the shape of the molecule. We only look at the molecule themselves whenever we're determining the structure. So this is considered to be bent. Okay, the bond angles are generally between 104.5 and 109.5, and that depends on how many lone pairs are attached to the central atom. Examples of this are sulfur dioxide and dihydrogen monoxide. So you see this is a bent molecule. Next, we have the trigonal planar molecule. That's if you have three bonds that are present. So you see something that's 120 degrees. An example of this is boron trichloride. Now, if you were to look at here, you don't see nitrogen here. Nitrogen would not be an example of a trigonal planar molecule. And the reason for that is whenever you have nitrogen, nitrogen has a lone pair on the central atom because it has 5 valence electrons. That lone pair on the side will actually push the other bond angles in and change the bond angles to 107 instead of 109.5. Because of that, you have this is called a trigonal pyramidal shape. Next, we have tetrahedral. Tetrahedral is when you have 4 bonds that are present. Examples right here is methane. You could also say, carbon tetrachloride or carbon anything. Carbon tends to be the one that goes to a tetrahedral shape. Next, we have trigonal bipyramidal. This is if 5 bonds are present, they'll oppose each other, and then you have different angles depending on which ones you're looking at. So for example, the bond between these two atoms is 90 degrees. The bond between these atoms is 120 degrees, and the bond between these two atoms is 180 degrees. It depends on which ones you're looking at as far as what the bond angle actually is. That's why there's multiple ones here. An example of this is phosphorus pentachloride, and you would say that this is an exception to the octet rule because it has the ability to bond to 5 things. That would mean that it has 10 electrons around its central atom. Next, we have octahedral. Octahedral is if 6 bonds are present, they'll oppose each other, and once again you get the same kind of setup, except instead of it being 120 degrees here, it should be 90 degrees there, just 90 and 180, because you have 90, 90, 90, 90, 180. An example of this would be sulfur hexafluoride. Once again, this would be an exception to the octet rule because if you were to look at sulfur, it would appear like sulfur has 12 electrons bonded to its central, or 12 electrons surrounding the central atom. So this would once again be an exception to the octet rule. There are multiple other shapes. You tend to get things like T shapes, and there's axe shapes, and there's all kinds of shapes that you can see depending on the distribution of lone pairs and bonds. In other words, what are the electron domains? Okay, the electron domains, the lone pairs aren't, they can manipulate the molecules that are there. Like I said, you don't actually take them into account when looking at the shape, but you would draw it with the electrons around it and then take the electrons away and say, okay, that's bent. This initially looks like it's trigonal planar, but whenever you take the electrons away, then you can clearly see that it's bent. This one looks like it's tetrahedral. Then you take the lone pair away and it's bent. So you can see how the lone pairs of electrons can influence the molecular shape. Example says, using the clear method, explain why the molecular geometry of water is bent and not tetrahedral. So if you were to look at it, remember we have the oxygen. It's going to have 1, 2, 3, 4, and then 5, 6, 7, 8. So its structure looks something like this. So if you were to look at it from the electron domains, we would say that its electronic geometry, taking into account all the electron domains, the electronic geometry would be tetrahedral. But if you were to look at the molecular geometry, we now remove these things and we say that this is clearly a bent molecule. So if we're using the clear method, we would say that it's bent. And then the reason why we would say that it's bent is because we would say water has 4 electron domains, but only 2 bonded atoms. So because of that, it's bent and not linear. Next, it says predict the polarity and molecular geometry of C2H2Cl2. So this has got 2 components. We want to predict the molecular geometry, and then finally we want to predict the polarity. So we would say C, and the reason why we know that is the carbons tend to attach to each other. That's what makes it kind of the basis for life. And then finally we have to bond 2 H's and 2 Cl's. Now how we draw this structure is actually going to determine the polarity. And let me show you real quick. So the first thing you're going to realize is I only have 4 atoms that I'm going to bond here. So I'm going to be short as far as connecting them is concerned. So the first one I'm going to do is I'm going to draw it like this, just as a basis, and I've connected all the molecules. But if you look, this carbon right here and this carbon right here are both not satisfied according to the octet rule. And I actually have valence electrons available, so I would actually put a double bond right there. So when I put that double bond right there, now this is an example of a particular molecule. If I were to predict the polarity of this molecule, I would say that it is a polar molecule. And the reason why I would do that is this chlorine right here is much more electronegative than this carbon. So if you were to look at it, there's a pole here and a pole here. When those two things pull, the up and down pole are going to cancel each other out. In other words, this component is going to cancel this component, but I have a net polarity this way. Now, the hydrogen is not nearly as polar. This is a nonpolar bond, so there's not a net pull in the opposite direction. So that makes this thing right here is going to have a partial negative charge over here, and there's going to be a partial positive over here. So this one, the way that I drew it right now, is actually called is a polar molecule. Now I'm going to show you how you can draw this in a nonpolar way as well. Okay, you can actually draw this as a nonpolar molecule if you take into account symmetry. So if I were to look at right there, if I were to put one hydrogen there and one hydrogen there, they would cancel each other out. The pull up, the pull down, they cancel. There's no net pull. I can do the same thing with the chlorine. Net pull, same pull upwards, they cancel out, there's no net pull. So because of that, depending on how you draw the molecule itself, that can affect its polarity. Okay, this is actually called trans. Whenever it's opposed like that, it's called trans when the 2 molecules are on opposite sides. Now the other one that we drew before was called cis. Now you don't need to know that, but you may see these terms later when we talk about cis-trans isomerism. Next, it says an element has to be a part of what chemical family in order to be the central molecule of an octahedral molecule. Now remember, octahedral molecule does not mean that it has 8 things connected. Instead, it takes the shape of an octahedron. So I have a central atom, and it connects to 1, 2, 3, 4, 5, 6 molecules. So you want some sort of element to connect to 6, let's call it Y, 6 different molecules. In order to do that, it has to have 6 valence electrons. So if you look at the column that has 6 valence electrons, that would be something from group 16, or you can call it the chalcogens. Although VSEPR is very useful in predicting the shape of molecules, there are some limitations to VSEPR. First of all, the shapes are not always the same depending on the bond length. If you were to look at the shape of a carbon bonded to 4 fluorines, the shape would be predicted to be tetrahedral, and it'd be pretty accurate, pretty close to that. But if you were to compare that to something that's combined with iodine, the bond angles are going to be slightly different because the iodines are so much larger than the fluorines. Because they're physically different in shape, you can't always use it to predict the exact angles between, but you can use them to get a pretty good idea. Also, VSEPR doesn't work for transition metals. Whenever you have multiple bonds and angles, realize that the more bonds there are, the greater the electron density is. So if you were to look at this particular bond right here between these carbons, you would predict it to be 109.5 based on the fact that it's tetrahedral. But then if you were to look, there's a lot of electron density here. So because this molecule, it could actually push some of these bonds further away because there's a lot of electrons there. The greater repulsive force could create greater bond angles even when it appears like it should be a tetrahedral molecule. Another thing for large molecules, whenever you look at large molecules, they have more than one central atom. You can't talk about the geometry of the entire molecule. Instead, you talk about the geometry of each central atom. So you'd say, okay, here's carbon number 1. Carbon number 1 should be tetrahedral. Here's nitrogen. Nitrogen number 1 should be tetrahedral. When I look at carbon number 2, it should be trigonal planar, and so forth and so forth and so forth. You can't talk about the geometry of the molecule as a whole if it has more than one central atom. So we want to review polarity. Remember, polarity of the molecule is affected by the polarity of each bond and by the geometry of the molecule. So in these particular molecules that we see here, there's a partial positive and a partial negative for each one of the charges. Now, if you were to look at the polarity as a whole, it's a nonpolar molecule. And the reason why it's nonpolar is because you can have a line of symmetry. And the line of symmetry, the line of symmetry says for every pull this way, there's a pull this way. For every pull this way, there's a pull that way, and they cancel each other out. So you've got to be aware of looking for lines of symmetry. Now, if you want to classify each bond as polar or nonpolar, now in order to do this, you would look at the change in electronegativity. Okay, so the bond right here between these two tends to be classified as nonpolar. So that means this is nonpolar and this is nonpolar. Now, the difference between carbon and oxygen is sufficient where it could be classified as a polar bond. So we're going to classify that as a polar bond. And oxygen and hydrogen could be classified as a polar bond. So if you were to look at it, we've classified all the bonds here as polar or nonpolar. Now, the last thing that you want to do is you want to look at the molecule as a whole. And you'd have to say, is there any symmetry between these? Yeah, this hydrogen cancels this one, but this oxygen and hydrogen are no longer capable of canceling each other out. So you would see that there's a net pull of the electrons towards this way, and so you would say this is a partial negative side of the molecule, which would of course make this the partial positive side of the molecule. So whenever you look at the molecular polarity determines the solubility of a molecule as well as the reactivity of the molecule whenever you're looking at the nucleophile. So right here, this right here is a nucleophile. Nu, it's not an element. It's saying that it's something that's negatively charged that wants to attract to a positive sort of molecule, a positive part of a molecule. And so if you look and see right here, this right here is a halogen. Okay, it's just any halogen, chlorine, iodine, something like that. And if you were to look, the nucleophile can actually attack this carbon right here because this is pulling the electron so much that it has a partial negative charge. That means this thing has a partial positive. So this negative charge can attract to that, and what happens then is it kicks off the electrons from the bond onto this, and now you've released the halogen and you've attached the nucleophile to this particular element. You can see how this mechanism or this reactivity could be very useful to chemists who are trying to build molecules given certain substituents. Valence bond theory. Valence bond theory, we're talking about as two atoms overlap, their orbitals overlap. So for example, when you have two hydrogens, remember these hydrogens are in the 1s orbitals. So I have a 1s orbital and I have a 1s orbital. Well, when those two overlap, instead of creating two 1s overlapping orbitals, you can say that they create what's called the hybrid orbital. So whenever you have, for example, these two overlap, it's an s and a p orbital, it's actually called an sp orbital. Okay, this is generally still called an S and this is still called a P, but you have an overlap that creates these hybrid orbitals. Now, whenever you overlap in bonding, remember that you don't want them to be too close, you don't want them to be too far. You want them to get to the point where it's the maximum attraction between the two. So the maximum attraction and repulsion. You don't want them to be so close together that the nucleuses repel, and you don't want them to be so far apart that they're not attracted. You want this minimum potential energy. Remember, nature is always trying to minimize energy. Okay, so that's why it reaches this level and it bonds there. Be aware of that. So this is a general guideline for you to follow, that nature is always trying to decrease the amount of energy. So we create what are called hybrid orbitals. If you were to look, you have the ground state of beryllium. The ground state of beryllium is this 1s, 2s, and then there's nothing in the p. And then you have the excited state of beryllium, which is 1s, and then we've promoted one of the electrons from the 1s to the 2p. Now this is possible because there's actually a very small energy difference between the 2s and the 2p. It's still there, but the amount of energy required to promote an electron to the next level is very, very, very small and can be occurred just by a collision between molecules. Okay, there's very, very little energy required to do that. So this actually allows us to say, remember when we said Be would bond to Cl2, and it looks like it's satisfied right here? Well, the energy difference between these is so small that energy is actually saved by promoting the electron to the next level and forming two bonds with something else. Okay, that's actually more stable. Another example of this is carbon. Now, when we talked about the Lewis dot structure of carbon, most people tend to draw it like this because it has 4 valence electrons. But remember, the ground state, the lowest energy state of carbon, is one in which you have 2 electrons that are there, and then 1 electron there and 1 electron there. So really, you're promoting an electron to the next level whenever you're trying to form 4 bonds. Okay, before we go forward, what we will discuss is a model. Okay, this is a model that works, and you're going to be taught it in chemistry and in college chemistry, but there's 0 experimental evidence for this particular model. It works mathematically, but we have yet to find any sort of verifiable physical evidence of it. And that's hybrid orbitals. So the overlap of an s and p results in a new, what we call, molecular orbital that we call an sp hybrid orbital. Okay, so you can create these hybrid orbitals from the combination of various orbitals between the two things that bond. Now, the assumption is that when you combine these two shapes, you get a new shape that we predict to be called the hybrid orbital. Now, there's something called an sp3 hybrid orbital. And an sp3 hybrid orbital is what happens with carbon, because carbon can form 4 bonds with four different hydrogen atoms, and so as a result, it's a combination of carbon's s and 3 of carbon's p orbitals together to form the hydrogen orbitals. So to make all of these energy levels equal, or all of these bonds equal, you have what's called a hybrid orbital as opposed to an s and an s overlapping, and then a p and an s. What happens is it creates a hybrid orbital which makes all of them the same energy. What about whenever we're bonding to 2 things? An example of this would be with nitrogen, or whenever carbon has a double bond. Because of the hybrid structure, this right here is still considered to be a single hybrid structure. So when carbon forms bonds with 3 bonds, this right here is bonded to 3 things. So I'm using my s, and I'm using 2 p orbitals to create what's called a hybrid orbital. That's why it's called an sp2 hybridization. Next, we call the sp hybridization, and if you notice, carbon's forming a bond with an s and a p, which makes it an sp hybrid. So the reason why these hybrid orbitals are possible is because it creates an average orbital between the two as opposed to what we saw before. So here's the energy level of the s orbital, and here's the energy level of the p orbital, and this is over dramatic. It's actually not much different. But whenever you do this, in creating a hybrid orbital, what you're doing is you're basically creating an average orbital that it makes all 4 energy levels equal. Now, if you notice, it's more towards the p orbital because there's 1, 2, 3 p suborbitals and only 1 s suborbital. So it's not going to be in the middle, it's going to be skewed towards the 2p orbital. So as a result of this, you have 1 electron each in the sp3. This is an example of what you see with carbon. Carbon has 4 electrons, 1 in each of the sp3 orbitals, which allows it to form 4 equal bonds. You see the same thing with whenever we talk about beryllium. Beryllium promotes 1 of its electrons from the, it has a 1, 2s, and then 1 in the 2p, and it can promote those electrons to make an sp orbital. Valence bond theory. Hybridization is a major player in the approach to bonding. There are 2 ways that the orbitals can overlap to form bonds. So this is kind of you have one which is called head-to-head overlap. A sigma bond is head-to-head overlap and is what always happens first. Okay, whenever you have a carbon bond to another molecule, let's say it's oxygen, a sigma bond or a head-on overlap always happens first. So I'm drawing the p orbital. See how they overlap? That right there is an example of a sigma bond because it's the head-to-head overlap of 2 particular bonds. This right here is what determines the molecular geometry and is the stronger of the bonds. So you have this cylindrical symmetry. So you can take it and you can kind of twist it, turn it, but at the same time it's stuck together as one kind of free to rotate bond. So the fact that a sigma bond is free to rotate and is the strongest of the bonds because it has this head-on-head overlap. Now another type, these are single bonds, And these sigma bonds are very energetically favorable. They like the overlap. So sigma bonds are the single bonds and require the most amount of energy to break. To break a sigma bond requires a great deal of energy. Now, it depends on the atoms and all that kind of stuff, but it requires more energy. There's a second type of bond that's called a pi bond. And pi bonds are characterized by a side-to-side overlap. So once again, I have my carbon and I've got my oxygen, and they overlap already in this orbital. But then I want to form a double bond between them. Realize that you have a p orbital that goes this way and a p orbital that goes this way. Now, I didn't draw it, but part of these two things are going to overlap. When part of those two side-to-side characteristics overlap, that's what we call a pi bond. Now, as you can imagine, this is not nearly as much overlap as you expected with a sigma bond. Okay, there's a lot less overlap. Because there's less overlap, it's easier to break this bond, and this bond is what we get when we get multiple bonds. So pi bonds are not as energetically favorable. They're the second or the third bond. So when I see here nitrogen, one of these bonds is sigma. The other two are pi from the side-to-side overlap. Okay, now pi bonds require a lot less energy to break because there's not as much overlap between them. But they still do require some energy. So when you're trying to break this thing, if you break one bond, you're breaking the pi bond first. Then you're breaking the second pi bond, and then you're breaking the sigma bond. Now, whenever you have multiple bonds in hybridization, when you have sp3, and this is only, we're talking about carbon here. Carbon is all we're talking about. sp3 indicates all single bonds. The reason why is you have carbon, 1, 2, 3, 4. So that's indicating the presence of 4 single bonds. When you have sp2 hybridization, that's indicating the presence of a single double bond. Now, when you have sp3, that indicates the presence of a triple bond. So based on the molecular geometry, you can predict the hybridization, or given the hybridization, you can predict the geometry. Okay, here's an example question. It says, rank the bonds from easiest to most difficult to break. So if we're looking at this, we're going to start with what we call the central atoms. Okay, this is going to be one of the central atoms. This is a central atom. This is a central atom, and this is a central atom. Okay, so if we're looking at this based purely on what we know, we're going to predict, first of all, that the toughest one to break is going to be this one. The reason why is the first pi bond is easy. The second pi bond is easy. But the third, the sigma bond, is going to be tough. Because of that, I've got 3 bonds that I've got to break in order to break this. So the triple bond is always going to require more energy than a single bond, because it is a single bond, but then 2 other bonds. And even though this is less, it's still there. This bond is going to be second, because I've got to break a pi bond, and then I have to break a sigma bond. So now we need to look at the rest of them in terms of how easy or difficult are the bonds going to be to break. You have a carbon attached to 3 hydrogens, and another carbon, and then you have a carbon that's attached to 2 hydrogens, and then double bonded to another carbon. So because of this, it's beyond the scope of this class to predict which one of these hydrogen bonds would be easiest to break from here. Now, you could probably predict based on what you know of electron geometry, but for now we're going to say that breaking this carbon-hydrogen bond is going to be the same as this one, which is going to be the same as this one, which is going to be the same as this one, which is going to be the same as this one. Resonance structures. We've already briefly touched on resonance structures, but molecules can have multiple arrangements of bonds and electrons. This is especially true with double bonds. Whenever you do this, there's a lot of ways that you can manipulate the structure by moving a pair of electrons to form a double bond, or taking the electrons away from a double bond and adding them to an element. Now, either one of these particular resonance structures are equivalent. We have no way of knowing which one it actually is, especially when you consider there's a negative charge here, which is very close to a negative charge there. Okay, but there are some resonance structures that are more correct than others. So you need to be willing to look at the formal charge to make sure the formal charges balance out. For example, if I had some sort of structure in which I had this was positive and this was negative, and then I had a negative, I would know that that would be wrong. There's got to be some way to cancel out that positive and negative and just leave the one negative charge. Resonance structures. All of these structures are equivalent, no way of saying which is accurate. So a lot of times what you do is you create what's called a hybrid resonance structure. So I said I have a double bond, I have a double bond, and I have a double bond. So because of that, what I can think of is I can think of like there's a third of a double bond there, a third of a double bond here, and a third of a double bond there. Well, if I think of it in those sorts of terms, I have a total negative charge of 2, and I have 3 atoms on which to split it. So you can think of these 3 equivalent structures, okay, these 3 equivalent structures, you have a hybrid structure that you see right here. This bottom middle element would be considered to be a hybrid structure because it's a combination of all 3. Does that mean that this is really what occurs? And the answer is no. But since these 3 structures are equivalent, and I don't know which one it is, sometimes you will see chemists draw it like this as a temporary sort of explanation of the resonance structures. Resonance structures. Resonance structures are delocalized versions of all resonance structures. The most famous one that you'll see is benzene. Whenever you see benzene, benzene represents a ring structure. Now each point on the ring represents a carbon. So benzene is C6H6. And if you were to look at this, you see the connectivity of it is such that when you have this structure right here, this carbon right here, actually let me draw it out a little bit better so you can see it. So it's going to be carbon, double carbon, 2 carbon. That's 1, 2, 3, and then we draw carbon. So this is what you see as far as the ring structure is concerned. So each one of these carbons can hold 2 additional electrons. But because of benzene, it has a double bond here and there. So each carbon can only hold a single hydrogen. So you see 1 hydrogen on each. Now there's no way of telling whether the double bond is actually here, as you see it drawn, or here, or here, or here. But if it's there, I'd have to cancel out the 1 double bond on the other side. So you have no way of knowing which one of these resonance structures is correct. So benzene, more than any other molecule, because it's so prevalent in organic chemistry, is actually drawn with a circle in the middle. The circle indicates the 2 resonance structures, and what happens is these pi electrons become what's called delocalized. So where these 2 pi orbitals are overlapping, the one next to it is also kind of overlapping. Kind of messed up my structure there. Okay, they all kind of overlap together. So what you have is you have a delocalized version in which all the electrons are kind of shared between the molecules. Now that references only the pi electrons, not the sigma electrons. So this is where we come to molecular orbital theory. And molecular orbital theory is an extension of hybridization based on the wave nature of the electrons. So whenever we look at the wave nature of electrons, we produce what's called a bonding orbital and an anti-bonding orbital. Now a bonding orbital is one that's lower in energy, and an anti-bonding orbital is one that's higher in energy. So bonding orbitals, whenever we look at a bonding orbital, the reason why it's lower in energy is the fact that the electrons can interfere in a constructive manner. So we treat one electron as a wave and the other electron as a wave. When they overlap at the same point at the same time, we have what's called constructive interference. Whenever you have constructive interference, peak overlaps with peak, you get a bigger wave and you get a more stable bond because the electrons are interfering constructively. Now whenever you have an anti-bonding orbital, that's when the electrons overlap peak to trough, and when you add them up you get a straight line. Because of that, that actually raises the amount of energy necessary to put electrons together, and you get promoted to where you have an anti-bonding orbital. Now generally we think of the s orbital as being kind of right here. There's the 1s orbital. The bonding orbital is lower in energy, so that's energetically favorable. The anti-bonding is above this, so this is considered to be an anti-bonding. It actually raises the energy. So bonding orbitals will actually promote bonds between the 2 atoms. Anti-bonding orbitals actually detract from the bonding capability. So if you have just the bonding orbital filled, yeah, you have a bond. But if you have the anti-bonding orbital filled, you have no bond. So here we talk about energy and bonding again. So remember, the energy of the bonding orbital is below the atomic, and the energy of the antibonding is above the atomic. So there's no net gain to an atom. So like say I'm a hydrogen atom, and I put one electron here and then one electron here. Well, I might as well have kept my electrons to themselves if I had two of them. Okay, helium's a better example. I would put one electron in the bonding and one in the antibonding, and then now there's no gain. I might as well just keep my electron. So if you have something where the bonding and the antibonding are filled, that tends to not form a bond. And then what we do is we calculate what's called the bond order. The bond order determines if a bond will form and determines how many bonds will form. So the formula that you have is 1/2 of the bonding electrons minus the antibonding electrons. And when you multiply it by the half that we originally said, that will actually tell you the number of bonds that form between two elements. So an example of that is if you have hydrogen, you have molecular orbital theory. It says 2 electrons go into a bonding molecular orbital. So I've got 2 electrons from 2 different hydrogens. Both electrons go to the lowest energy state, okay, because we always fill from bottom to top. And because of that, there are no bonds in the antibonding. So the antibonding is empty. Okay, because it's empty, there tends to be a bond that forms between hydrogen and hydrogen. So we get H2. The bond order is 1 because when I do 1/2 of the 2 electrons in the bonding orbital minus the 0 in the antibonding, that gives me 1, which indicates there's one bond between these two hydrogens. Now when I look at helium, I've got 2 electrons in each. They first both contribute 1 electron to the bonding orbital and 1 electron to the antibonding orbital. Because of that, there is no net gain in in energy. So because of that, the atoms tend to not form bonds, and that's why you don't see this in nature. This does not occur. Okay, so that's why noble gases tend to not form bonds with other molecules, because they don't gain anything out of it energetically speaking. Remember, nature wants to lower the energy as much as possible, and that doesn't happen here. So since that doesn't happen, this doesn't actually work. And if I were to calculate the bond order, I would say 1/2. I've got 2 electrons in the bonding orbital, minus I've got 2 electrons in the antibonding. 1/2 of 0 is 0, so there are 0 bonds that form between these particular substances.